Hello PCH students, Flange here. This is our last lesson for chapter 1 and it's on quadratic models. It's basically using what you know about quadratic functions to come up with some application problems. Our first one is something you've seen in physics already. Do you remember this equation from physics? That displacement S equals 1/2 a t squared plus initial velocity times time plus initial displacement. Well, it's quadratic because of the second degree equation on there in time. So now, I don't expect you to memorize this for math. You will eventually for taking your AP test. So I'll always give you this equation. You have to know, though, be familiar with these terms like acceleration, initial velocity, displacement, and time. So you can use something like this to answer, let's say, how fast stop. Okay, so a ball is thrown up from a cliff, 100-foot cliff, with an initial velocity of upward velocity of 60 feet per second. When will it hit the ground? Let's try and illustrate this with a picture. Here's the cliff, 100 feet off the ground. And we throw the ball up like this, and it comes back down again. Now I showed a little horizontal displacement, but I just want to make sure you can see the idea here that it's basically going straight up and straight down. I stretched it out a little bit there. And it's being thrown up at initial velocity of 60 feet per second. It's 100 feet off the ground. When will it hit the ground? Okay, let's find out. So it's going up at 60 feet per second. So from that equation we had before, the acceleration, I'd give this to you as negative 32 feet per second squared in the English system. You'd have to know that the initial velocity is 60 feet per second, positive, because it's being thrown up. We can set up a reference level of this being 0. So our initial displacement is 100, and we want to know when we get a displacement of 0, 100 feet. So we go ahead and put that into the formula. Displacement equals 1/2 at squared plus initial velocity times time plus initial displacement. So 0 equals 1/2 times negative 32 t squared plus 60t plus 100. And we go ahead and solve that. Okay, and I put the values in, and we're trying to solve it, and check this out. It factors 4t, t, 5, 5. Let's make this one negative and this one positive. Yeah, negative 20 plus 5 is negative 15t. So you get t equals negative 5/4, or t equals 5 seconds. So the only one that makes sense here is at t equals 5 seconds. Negative time doesn't make sense. Why is it giving us that answer? Well, because if you look back up here, it's assuming that you started from down here. So yeah, we might have had this as one of our answers. That makes sense. T equals 5 seconds is when it lands. But we're also seeing this other answer at negative 5/4. T equals negative 5/4. It's assuming the cliff wasn't there and that you actually shot it from down here at a greater speed, at higher than 60 feet per second, and then we'd get sort of a similar path over this way as it came down. Okay, next example. Real gem, maximum revenue. A small theater has a seating capacity of 2,000. When the ticket price is $20, attendance is 1,500. For each dollar decrease in price, attendance increases by 100. What ticket, first of all, write the revenue R, and then what ticket price will yield the maximum revenue? What is the maximum revenue? So let's take a look here. Write the revenue, R of the theater, is a function of ticket price X. Well, let's let the function of X, which is going to equal the number of $1 decreases. So when we're going to part A here, to get revenue, revenue is going to be number of tickets times the price per ticket. Number of tickets times the price per ticket. And it's easier to do these in terms of X now, because the price per ticket is going to be $20 minus X, because for every $1 decrease, we're going to subtract that from $20, the original price. Now the number of tickets, though, as we decrease the price, we get more people signed up. For each dollar decrease in price, attendance increased by 100. So we might have started off with initially 1,500 people, each paying $20. But now we're going to add on 100 people for every time we lower the price by $1. So that's number of tickets is 1,500 plus 100x. That's an increasing function. And the price is a decreasing linear function. And we multiply the two together, we get a revenue function, which is a quadratic. Now, what ticket price will maximize the revenue? Well, let's take advantage of the factored form here. We can find the roots here, and the roots are going to be when r equals 0, when we get no revenue. 1,500 plus 100x, set that equal to 0. Divide by 115 plus x equals 0. Add x equals negative 15. And our other root, 20 minus x equals 0. X equals 20. What do these two things mean? Well, at x equals 20, we've basically lowered the ticket price too much, and we have no income because we're not charging anything per ticket. At x equals negative 15, we've basically gone backwards and increased the price so much that now nobody wants to come. So the number of tickets goes down to 0. These two form the roots of a sad parabola. I know it's sad because the leading coefficient is going to be negative. Look at the expansion here. If we expand this out, we're going to get negative 100x squared. This is where though the factored form for the quadratic is handy. It's going to go like that. Here's our x, and here's our revenue. And halfway between the roots, then, will be our maximum revenue. So, the average of the roots. Remember that trick from doing factored form? So, that x would be negative 15 plus 20 over 2, or 5 halves, 2.5. So, basically, $2.5 increases. See what the questions ask. What price will yield a maximum revenue? What is that maximum revenue? So here's the point. We do the price will be, as we said, 20 minus x. So that's 20 minus 2.5. So we should sell tickets for $17.50. That price should maximize the revenue. And what will that revenue be? Let me get out my calculator. Okay, did the calculations. The max revenue is going to be when we put $2.5 decreases in there. So I put 2.5 over x into both these equations, and I came up with $30,625. Wow, that's a lot. Now, one thing to be careful of this, it was mentioned that the max capacity was 2,000. Did we exceed that? Let's head on down here and find out. Our final capacity was 1,750, so we haven't exceeded the max capacity, so we can go with this. If you found that the peak of the parabola ended up going past your maximum capacity, you got to be careful. Now, this is not capacity down here. This is x. Capacity is 1,500 plus 100x, the number of people that you have in there. Okay? All right. Flange out. Out.